Hey y'all, welcome back to a Robinson rant. And yeah, let's get going. Last time I was talking about the complex plane and specifically the idea of taking a oscillatory motion, a periodic motion, and converting it into an expression e to the j omega t. In other words, if you have something like a sinusoidal variation, you could think of writing this as you have actually two options: j e to the j omega t. Or if you prefer, you could also write this as e to the j omega t minus 90. I'll put pi over 2. Pi over 2. So you have a couple different options there. Of course, the same thing with cosine of omega t. The idea that we could write this as e to the j omega t. Keeping in mind that we've introduced an extra piece, and so at the end we might have to remove it. So let's go ahead and take advantage of this. Let's see how will this help us moving through our circuit analysis. So let us first consider, and we'll start off with a time-varying potential connected to a resistor. Okay. So we'll call this resistor R. We'll say that the potential, the source potential as a function of time, let's go ahead and call this cosine of omega t. And I want you to go ahead and get me an expression for the current as a function of time running through the resistor. Go ahead. You got it? Yeah, good. Okay. Now, of course, you have two different ways of going at this. One way is that you say, okay, I'll just apply Ohm's law. I have a potential drop across the resistor, call it VR. That is equal to the current through the resistor times the resistance. And therefore, I have a function VR, that's the cosine of omega t. I divide that by R, and that gives me my current as a function of time. And I'm done. And I say you have two ways of going at it, but essentially it's the same thing. What you could do is say, okay, well, I will express VR rather than a cosine of omega t, I will express it as e to the j omega t. Then I'll apply Ohm's law. VR equals IR R. And then I'll divide it by R. E to the j omega t divided by R equals IR. And then at the end of the day, I'll take the real component. So I want the real piece of this. And so I end up with, again, the cosine of omega t divided by R. I know, it doesn't seem very enlightening. I understand. Let's try something a little different then. You ready for it? And here's where some of the cool surprises come in. So let's go ahead and do the same idea. We'll do a time-varying potential. And now, why don't we go ahead and hook this sucker up to a capacitor. Okay. So take a moment, okay, see if you can get the expression for the current I guess you could do the charge as well, but the current run, let's say the current running through the capacitor. You got it? Yeah, good, good, good. Okay, so we have our potential as a function of time. Let's go ahead. We'll leave it as cosine of omega t. Okay. And so again, we need to relate somehow the cosine or the applied potential to the current. So we go to our handy dandy equation. We know that the potential of a capacitor, the drop, is given by the charge on the capacitor divided by the capacitance. I don't think that's any surprise. So we could go ahead and throw this in. We get cosine of omega t is equal to Q over C. You say, well, I want the current going into the capacitor, and so I need to take a time derivative. And so we end up with something that says omega sine of omega t equals I, the current flowing through the capacitor, divided by C. And last but not least, we notice that if we move the C to the other side, we get omega C sine of omega t equals IC. That's kind of cool, right? What do you notice that's kind of different there? Thinking about the applied potential for a moment. Yeah, let's look at this. This is kind of the cool thing about AC circuits, and we'll delve into this a little more. But look at this. The applied potential goes like cosine. And yet the current running through the capacitor goes like sine. That's kind of interesting, actually, right? If I were to plot as a function of time, that's good enough. And then I'll go ahead and do my current. Okay. Notice it's scaled, right? So rather than being at a height of, say, 1, I guess I left this as 1, this will be at some different height, omega c. Okay. I'm going to plot these both on the same just so we can see the change. Okay. But let's see, it starts out at 0, and then it should peak, and then go to 0, and then it should have a trough. And so you see that the capacitor is shifted. The value of the capacitor is shifted by a certain amount with respect to the applied potential. So I guess a different way to say this, the response of the capacitor is shifted with respect to the applied potential. And you can see the shift as well, right? You see that it's shifted pi over 2 degrees to the right. In other words, you could write this as IC equals omega times the capacitance. And if you prefer, you could write this as cosine of omega t minus pi over 2. Right? That takes care of this shifting if you want to present everything as cosines. It's kind of cool. So now let's go ahead and think about what happens if I treated this using Euler's relation instead. So let's see if we get the same result. So let's go ahead. If v of t is equal to cosine of omega t, omega t, and I will go ahead and now, rather than thinking of only a real part, I'm going to think about a real part with this imaginary part entered in. And then afterwards, I'll remove that imaginary part. Okay? So it's kind of the add it in, make your life easy, and then remove it later. So this kind of reminds me of that technique of completing the square. So if you remember, sometimes you're asked to complete the square. So you have some expression, you add in an extra piece to complete the square, and you subtract that piece off as well at the same time. And so it kind of reminds me of that. So I'm adding in this imaginary piece to allow me to express v of t as e to the j omega t. So you can think now that voltage, because I've added in that extra piece, you can now think of that applied voltage as being this arrow rotating in the complex plane, with the length of that arrow being 1. Well, now let's go ahead. We have our potential across the capacitor is equal to Q over C. And let's take this idea and we'll plug it in. So we have e to the j omega t equals Q over C. We're interested in the current, so we'll take a derivative. So now when I take the derivative, notice I get that j coming down in front, right? J, although special, is just another number. And lastly, I'll multiply through by c. So we get this idea, j omega c e to the j omega t equals IC. And if you wanted, you could always back sub if you want, right? Okay, so we have this expression now, and now we have to be careful. Remember, I said you take your expression, you add in this imaginary piece, you do the calculation, and at the very end, you take out the imaginary piece. Okay? If you stop right here, you won't get the right answer, right? You say, oh, this whole thing is imaginary, and I'll just strip it off. No, don't forget, there's imaginary number tucked into this idea. So what you'll have to do is apply Euler's relation. And I'll write it out here. Cosine of omega t plus j sine of omega t equals IC of t. And we multiply through by j, and we'll get the imaginary term separate from the real term. And so we get a j times j, which gives me a negative omega c sine of omega t. And then we have a term involving only imaginary numbers, plus j omega c cosine of omega t equals IC of t. And now that we've successfully separated out terms involving the imaginary number and terms that are real, we say this term, when we introduced j sine of omega in the potential, that resulted in this term appearing in our final answer, right? We're kind of using that j to remind us of what things don't belong in our final answer. And so at the end of the day, we can get rid of that. And so our final answer is negative omega c sine of omega t equals IC of t. Well, let's go on for the third one. You probably know what's coming up. Go ahead and do this third idea. Do the AC current applied to an inductor. And find the relation, give me the response of the inductor as a function of time. You got it? Yeah, good. So I'll go ahead and let's go ahead and we have that the potential of the inductor is equal to L di dt. And I'll go ahead and I'm just going to use the Euler relation. So I'm going to use the V of t is equal to EJ omega t. And hopefully, again, you see that it's helpful, EJ omega t, partially because it's really stinking easy to do that integral. So I'll call this di, and we have the 1 over L, and we need to integrate this sucker. And, okay, well, what happens? I end up with a 1 over j omega L e to the j omega t equals I. And again, we need to be careful here. Okay? If we just say, okay, get rid of the j's, that is going to give us 0. That's, I mean, at first blush, you might say, okay, this is 0 because I got to get rid of those imaginary components. No. Okay? You have to remember about doing Euler's relation and multiplying through and yada, yada, yada. Okay? So here we go. Let me, for a moment, first of all, let's get 1 over j. Call me crazy. This is like compound fractions. I hate compound fractions. Anytime I see one, I want to turn it into a regular fraction. Okay? 1 over j for me is the exact same the exact same thing. Okay? I don't know why, but I always like to have it j's in the numerator. And really, for this to kind of make sense, it just helps out. So you can think about if you have j in the denominator, that's the same as having a negative j in the numerator. Okay. So I like having this written not as 1 over j omega L. I prefer to write this as negative j over omega L. And of course, we can use our Euler relation again. Sorry, I keep hitting the delete button with my finger. We can multiply through, and again, you see what happens. We get a 1 over omega L sine of omega t minus j over omega L cosine of omega t equals IL of t. And we say, well, this is the imaginary piece. We introduce the imaginary piece into the potential. That results in an imaginary piece in the current, which we don't care about. And so I find that my final current is given by sine omega t equals IL of t. So let's take a minute and let's look at this. Right? This is interesting. We have our applied potential, which is given by cosine of omega t. And if we look at the response of the current through the resistor, we just had the same thing, cosine of omega t. We had this scaling factor of 1 over r. For the capacitor, we had this cosine of omega t plus pi over 2. And again, we had the scaling factor of omega c. So I'll leave that out. And we had this IL equals cosine of omega t minus pi over 2. Again, with the scaling factor of 1 over omega L. So let's go ahead and plot these. I find this really fascinating. So let's go ahead and plot these. And first off, I'll plot time. I'll call this I, the current. And notice that the current through the resistor and the applied potential vary in exactly the same manner. Okay? This is what's sometimes referred to as in phase. In other words, there is no angular shift between one and the other. So we get this nice, well, terrible looking cosine function when drawn. And so the red is the current through the resistor. But let's take a second. Now let's look at the current through the capacitor. And so we notice that we have a shift between, I'll put IC here. We have a shift, a difference between the applied potential and the resulting current. It's kind of interesting. And we say that it leads. Right? You can see that the current through the capacitor peaks before the potential. Right? So if you have this AC potential, the current through the capacitor peaks prior to the potential peaking. So we say that it leads. Of course, on the other hand, you can see also for the inductor, it does not peak until after. So the inductor will look like, so we see that the inductor with respect to the applied potential, we see that it peaks after the potential peaks. And so we say that the inductor lags the applied potential. And so that's you see, that's an interesting relationship, is that we can start to dictate by our choices of the inductor, we can start dictating when the inductor current peaks as opposed to the applied potential. You can start introducing a phase difference. We call a phase difference. The second thing I'm going to point out to you, very important, notice this scaling factor. For the resistor, it just deals with the value of the resistor. For the capacitor and the inductor, you notice that not only does it depend on the value that you choose for the circuit element, but it also depends on the frequency, the angular frequency of the applied potential. This, by doing an AC circuit, you actually change the magnitude of the output current. You can see for an inductor, if you do a high angular frequency, the current running through the inductor drops to zero, right? As omega increases, the current through the inductor goes to zero. That should hopefully make sense. From a physical standpoint, do inductors like changes in current or don't like changes in current? They don't. So omega represents how quickly you're changing the current. If you're changing the current really fast, the inductor says, whoa, 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 I don't like this. And it will respond to prevent current from flowing. Whereas a capacitor, if you're changing capacitor really fast, if you're changing that, what happens? Well, the capacitor doesn't ever fully charge up, right? If you're changing the applied voltages really fast, the capacitor is charging, discharging, charging, discharging, charging, discharging. It never gets fully charged. And so it will have a lot of current flowing through. And of course, you can flip it. As omega goes closer to zero, the capacitor starts acting more and more like a brake. Current drops to zero. And physically, that's because you're giving the capacitor time to actually be fully charged, and then fully discharged, and then fully charge again. And when it hits that fully charged, it's not going to have any current flowing through it. Whereas the inductor, as you see, as omega goes down to zero, more current flows through the inductor because it can act like a wire now. It sees a very gradual change and it says, okay, I'm okay with that. It's not very rapid. Cool. No, maybe. Okay. Yeah, it's really cool. Okay, so let's go ahead. There's a last thing I want to introduce today, and I'll call it impedances. And if we go back and look, we said our applied potential V, we wrote that as e to the j omega t. And we went through and turned the crank, and for the resistor as a function of time, we found that we could express that as j omega t divided by r. Or if I take that and substitute it back in, you notice that we get something that says the current through the resistor as a function of time can be expressed as the applied potential divided by R. Right? Well, let's take a look at, for a moment, of course, you know this as Ohm's law. Let's take a look at them for a moment regarding the capacitor. For the capacitor, we had something that said J omega C e to the J omega t equals the current through the capacitor, the time varying current. Well, let's go ahead and take that substitution again. And what do we get? We get J omega C times our potential, our source, equals IC. What do you notice there? Yeah. Let me spell it out. By expressing the potential source using Euler's relationship, we find that we can model the capacitor as a linear relationship between the applied voltage and the current. In other words, we have now turned a differential relationship into a linear relationship, right? If I had not used Euler's expression, you would have had I is equal to, well, we had this negative omega c sine of omega t. And it's hard to see the relationship between I and V. But if we keep those imaginary pieces in for the moment, we now have a linear relationship between the current running through the capacitor and the applied potential. It looks a whole lot like Ohm's law again. So I'm going to move this to the other side just because we think of the applied potential. And this term in front, this constant of proportionality between the applied potential and the response of the circuit, is the impedance of the capacitor. And we give that the label Z. And I'll label it C. Of course, we could also do the inductor. So the inductor, we had negative, okay, maybe I shouldn't have done the negative J over omega L, e to the j omega t is equal to IL. And so again, if we substitute in, we have our potential equals omega L over negative J, okay, IL, or the potential is equal to J omega L. So maybe I shouldn't have moved that to the denominator. I forget. And again, notice this is a constant of proportionality between the applied potential and the current. And so we define that as the impedance of the inductor. Of course, what's the impedance of the resistor? Yeah, it's just R. Yeah. Okay, so you ready for it? If we have an alternating potential, an AC potential, or an AC current if you prefer, if we have an alternating source, and we choose to express that alternating source using Euler's relation, then we can treat our circuit elements as having impedances ZR, ZC, and ZL. And notice that the relationship is linear between the current and the applied potential. We can therefore add impedances according to the rules that we developed for resistors. I'll say that again. If we take an AC source and model it using Euler's relation, then we can treat each circuit element as having its respective impedance. And because of the linear relationship between the applied potential and the resulting current when expressed as impedances, we can treat all of our circuit elements like resistors. Let me give you an example, okay, off the cuff. And then, so we have an AC supply. We'll call it voltage, that's fine. And let's go ahead and put a capacitor And let's put a resistor in here. Yeah, let's just go for all three. Okay. And we'll say C, we'll give it this an R, we'll give this an L. And we'll say that the potential is some amplitude cosine of omega t. Okay. So I said if we express our potential in terms of Euler's relation. So I will go ahead and model this as V of t equals V naught e to the j omega t. Okay. So now I have expressed my potential as Euler's relation. So when I do that, I can now think of not C, R, and L, but I can now think of those as acting as impedances. So, and I think that usually what you do is you just put a box. I think you just put boxes around them. This is so that you don't confuse it with any other circuit element. Okay. And the question then becomes, how do resistors in series combine? Yeah, they add. So the total impedance of the circuit would simply be the summation of the three impedances. And so the current running through the circuit. The current running through the circuit as a function of time will simply be V naught e to the j omega t divided by ZC plus ZR plus ZL. Technically, we're done. I guess you could argue, well, wait a minute, Greg, we still need to get rid of the imaginary stuff. And I completely agree. So you do still have a bit of algebraic work to do. So we still have a little work to do. But notice we're not playing around with differential equations and doing all these integrations anymore. We are doing straight out algebra. So let's finish this sucker. Might as well. Off the cuff demonstration. Let's go ahead and finish it. So I have V naught e to the j omega t. I have R plus j. I'll put omega L minus 1 over omega C. And now I want to get my personal preferences. Let's go ahead. In order for us to be able to separate out the real component from the imaginary component, we need to get the imaginary component out of the denominator. So how are we going to do that? I am going to multiply both top and bottom of the equation by the complex conjugate of the denominator. In other words, I'll do this again. This is why I introduced the complex conjugate, not to make your life difficult, because it's actually useful here. I'm going to replace j with negative j, omega L minus 1 over omega C, divided by the complex conjugate. And so we end up with V naught e to the j omega t R minus j omega L minus 1 over omega C. And let's look at the denominator. What do we have? R times R, R squared. Plus j times R, minus j times R. So the cross term disappears. And so we have something that says r squared plus, oh, excuse me. Yeah, negative j times positive j gives me a positive. So I get r plus omega L minus 1 over omega C squared. Okay. And what do we have in the numerator? Well, there it is. Now our last step, now that we have gotten rid of the j in the denominator, our last step is to expand e to the j omega, get the imaginary terms by themselves, and throw it out. So what do we have? We have v naught cosine of omega t plus j sine of omega t times rigmarole r minus j omega L minus 1 over omega C all over r squared plus omega L minus 1 over omega C squared. So yeah, now we have to do some more cross multiplication in the numerator. And eventually you probably won't have to actually do that. Okay, most people, they'll start here, or they'll get here, and they'll just write down the next step. They won't do the cross multiplication. They'll say, okay, well, this has to be multiplied by cosine, this must be multiplied by sine, and then they write it down. So you get I of t, I'll do the whole thing here. You get v naught cosine, I'll go r cosine of omega t. And then I have positive, negative, so I get a positive omega L minus 1 over omega C sine of omega t. Okay. So there's my real part. Then what do I have added onto that? I have plus j. I guess there's a v naught there too, excuse me. I'll say v naught j r sine of omega t minus omega L minus 1 over omega C cosine of omega t. Yeah, so you need a big piece of paper. Okay. And then we have r squared plus omega L minus 1 over omega C squared. And now we're finally there. We say, okay, we introduced that imaginary piece at the beginning. We're going to pull it out at the end. And so I of t is equal to, look at this rigmarole, v naught r cosine of omega t plus omega L minus 1 over omega C sine of omega t all divided by r squared plus omega L minus 1 over omega C squared. Ta-da! Now I know that you had to do a little bit more algebra, okay? But I would argue that doing the algebra is a lot more fun. Fun might not be the right word, but a lot easier than having to deal with the differential equations. Okay, so that's number one. The second thing I'll point out again, and I can't emphasize this enough, notice that these impedances are linear, okay? Which means, although I did a RLC circuit in series, okay? I did an RLC circuit in series, but you could still apply your matrix techniques. I didn't have to do it in series. You could do, some rigmarole with all of these circuits. Okay? If you model them as impedances, you can then apply your matrix techniques to solve the circuit. In other words, if you understand this lecture in terms of impedances, then all of your chapter 3 materials can now apply to AC circuits. And furthermore, not only do they apply to AC circuits with only resistors, but they can apply to any AC circuit involving resistors, capacitors, and inductors. In other words, this one lecture takes care of all of one chapter. You already have all of the techniques. I just have to introduce this idea of the imaginary number. Pretty cool, huh? Okay, I think that's enough for today. We'll start doing some more example problems. We'll get our intuition built up about this complex plane and using the imaginary numbers. And yeah, we'll keep at it. Hey, thanks for your attention. I'll see you next time.